Okay.
Alright, so this is a voltmeter. What if we want to measure instead the current? We'll do the same thing, but I'm going to put the meter here. Notice that the ammeter is in series, where the voltmeter is parallel. And while I'm on that subject, let me just throw in something I might have mentioned earlier, but I know I didn't, so I should have and didn't. If I had a parallel circuit, what is distinctive about it is all three branches have the same voltage, and the current through each branch can vary. I1, I2, and I3 can be different, but voltage is always the same. And if I had a series circuit, the current through all three is the same, but the voltage, V1, V2, and V3, can differ. All these voltages have to add up to this voltage. All these currents have to add up to this current, or I should say, that current, the one that goes through all three branches. Why? Because Kirchhoff's law said so. This is one node here. This is one node here. All the current flowing into the node has to flow out, so this current has to equal these three put together, and these three put together has to equal the return path current. With the voltages, this voltage that goes up has to equal these voltages going down, so that they'll all add up to zero. With the meters, what you're recognizing is if you're going to measure current, the current has to flow through the meter. When you're measuring voltage, and by the way, what I just said is sort of a conceptual thing. It really does flow through the meter, but it also flows through the meter when you have a voltmeter here, but it flows through differently. What you have with a voltmeter is the same thing. This meter and this meter are the same thing. They're called a galvanometer. Which is really a low current measuring instrument. It responds to current flow. It doesn't care about voltage. It cares about how much flows through it. So how does a galvanometer end up measuring voltage? If you put a large impedance here, I could say large Z, but I'll just say large R, because it's really going to be resistive, then all this current flows through here, and a tiny little bit flows through this guy. And that's all you need to make that meter turn. Now what about this guy? You got all the current flowing through here? Not how it works. What's really inside the meter is a thing called a shunt. What's really going on is you got a galvanometer, but there's really two halves to it. One is this thing here called the shunt, and the other is this thing here called the galvanometer, so to speak, which takes a tiny amount of current to work. So how do you make that happen? Make this thing a low resistance. Where this thing was a large one, this one is a small one. If you have a small resistance here, almost all the current is going to go through this path right here. Very little of it is going to go through the meter. If you have a large resistance here, very little current is going to go through this meter. Most of it's going to go through the main branch, because most of the voltage this guy, and very little across this guy. I should say, most of the voltage that would have been the same as this will drop across here, so this voltage divider has very little voltage driving very little current through this meter. That's the difference between a voltmeter and an ammeter. The same basic instrument, except with a voltmeter, you've got a series high impedance. With an ammeter, you've got a low parallel impedance. Otherwise, they do the same thing. And that's essentially what we do when we measure AC or DC. I should say voltage or current. Okay, what about AC or DC? Does it matter? Well, it depends on what you want to look for. Do you care about what the waveform looks like? Or you just want to get some numbers and say, okay, I know what the waveform of the power coming out of the wall socket is. I just want to know just how much is there in terms of voltage. Or if I have a load, how much is flowing through that in terms of current. Is there any real physical difference between an AC and a DC voltmeter? Yeah, actually there is. It works like this. You got a coil, and you got this thing connected to your pointer. When current flows through here, and you get a magnetic field here flowing through this coil, it affects the magnetics. Since this is a north and a south pole, and there's a spring, it kind of makes it want to go back to zero. The current flowing through here makes this magnet want to turn, and it works against the spring that makes it want to go back. That's how a DC meter looks. This guy here is a permanent magnet. So it really matters which way the current flows, and eventually means if it flows both ways, like AC does, it's not going to work. It's basically going to spend as much time in the positive as it is in the negative sense. And when the meter starts going this way, it's going to be undone by the other half of the cycle. It's going to make it go the opposite way. So how do you measure alternating current? Well, you start out with the same concept, but the thing that is attached to the needle is another coil, and it's wired essentially so that the magnetic flow here and the magnetic flow here will actually work against each other. And when the current flows one way, it will turn. And when it flows the opposite direction, it will still turn, because they would have the same kind of forces applied to the needle. So you might ask yourself the question, well, you know, why not just use an AC meter to measure DC since it'll work? The answer is you could. But the thing about it is that it's much easier to make this work more accurately. With AC meters, there aren't as many steps, meaning you can't measure large currents or small currents. Usually design it for the one you want to do. With DC meters, it's easier to do that because the galvanometer effect is pretty consistent. All right, so you know, that's the best answer I can give. There may be other reasons, but that's the one that always occurred to me as the reason why AC meters don't do such a good job measuring DC. But they normally would think could, because they don't care if the current's going this way or that way. They're still going to deflect in the same direction. They do use that, by the way, that design that's used for the AC meter, if they want to have a center off, if it's zero, so that the needle will go this way if you got a plus current flow, and this way if you got a negative current flow. Once upon a time, your car used to have an ammeter in it that would show you whether you're charging or discharging, depending which way the needle works. Nowadays, they don't use ammeters because it doesn't give enough information. It tells you what currently is the direction of flow of energy into the battery or out of the battery, but not how much. The reason they use a voltmeter in your charging system in your car is that the voltage can be interpreted as a way to determine the condition of the battery. If you've got yourself at 14.2 volts, which is about as high as it ever goes, you're charging the battery at a maximum rate, and then it'll go through what they call float range because of the way storage batteries are designed in the maintenance-free mode nowadays. And then it drops down to 12 volts when the charging system shuts off, because the battery with no charging system attached to it will produce 12 volts, 12.6 to be exact. When the charging system's at full, it's 14.2 if it's in the 13 range. It's charging, but not at the full rate. So looking at that voltmeter, you get a little bit more information that's useful on the condition of the battery, whether it was discharged, whether your charging system's really working. Just to see how much current's flowing in or flowing out doesn't give you all that. So they've gotten away from ammeters and they've gone to voltmeters on your cars. Okay, that's normally what you do with a meter that has a needle. This is a so-called analog.
Was it Simpson, I think, was the popular one?
Yeah, the most frequently, glad I got an audience, even if it's our cameraman, most popular model is the Simpson 260. The old workhorse in the industry. I got a couple of them at home, and they still work and I still use them. The question is, why do people still use those instead of the ones that you more frequently see out in the field, which is usually made by the RL Fluke company? Oops, I gotta watch my spelling here. Fluke makes yeah, right, we're trying to keep this a family rated.
YouTube channel is family rated.
Yeah, this got to be family rated. Okay, it's usually the number one or no number one, followed by digits 3, 4, 5, depending on how much of an accuracy, how many significant digits you want to display. If you're looking at 125 volts, you really don't care if it's 125.6735. We've learned in science 3 digits is usually significant enough. Sometimes 4, I don't know why, but you took chemistry in high school. What was Avogadro's number? It was 6.023 times 10 to the 23rd. Well, 10 to the 23rd means you had 23 zeros after that 6.023. Did you care if it was 6.023 blah, 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 blah? No, you didn't. When you did those problems using pi, you usually remember pi was 3.14. You didn't care that it was 3.1415926535899793, which, by the way, is what it is to 15 places. I just happen to remember that. It's not significant. When you use the slide rule, you didn't, but I may have. Back before calculators showed up, science calculators showed up about 1972. So I remember the first one that came out from Hewlett Packard, HP. What was it? The number they put on that model. The 12 was the one that they did for business, and the one they did for science, yeah, it was the HP 35. $400, $395. I'll tell you, in 1970, that's a lot of money. I couldn't afford it, so maybe a few years later, the Bomar Brain and a few other cheaper calculators came along, and then TI came out with the models, all kinds of models, the 50, the 51, the 52. And then they became reasonable. For less than $100, you could buy a really good calculator that did just everything. And they gave you a lot of significant digits, maybe 8 or 10 or 12. But you only cared about the first 3. Just like when I used the slide rule, that's all the accuracy you could get out of it. They called it SRA for slide rule accuracy. Most meters are like that. So when you buy a Fluke meter that's got a digital display where you see the actual numbers instead of a needle flying by a scale, that's all the digits you need to really get information that's worth having. So what do they do inside to do the conversion? I'm not going to get into too much detail on this, but they do an analog to digital conversion. And when you want to go digital to analog, it's pretty easy to talk about, because what you have are current switches. Basically a bunch of transistors, and they turn them on one at a time, and each one is got twice the current flow as the one before it. So you produce a binary result that's This one's gonna be 2 to the 0, and this will be 2 to the 1, this will be 2 to the 2. Basically, you're gonna come up with a system that produces numbers based on which ones are switched on. Now that's digital to analog. What about analog to digital? Actually, you have to go digital to analog in order to produce analog to digital. And the reason has to do with the way the process works. Nobody's come out with a really good analog to digital system. So what they do is they use a comparator. They turn on one of these guys, and then they compare it to the voltage it's trying to sense. And when the two compare, meaning they're equal, they stop and they say, that's the binary number we're looking for. So it's a ring counter, it's a tracking system. And I didn't cover the transistor very well, so maybe I can cover that tonight if we have the moments, and I think I'll make an effort to do that. So that's how this thing comes into being. Does the same thing as the analog, it just displays differently. You get actual digits rather than having to look at the needle and look at the scale behind it and figure out the numbers. Okay, so much for the standard way of doing it. If you've got a signal that's not sinusoidal or direct current, another instrument might be useful. And that one is the oscilloscope. And we've talked about that a little bit, saying, okay, that's how we measure things in the time domain. Let's get a little more into detail on this. The oscilloscope, of course, is a derivative of the word oscillator, which means you're looking for things that change periodically over time, like one of these guys. And what you do in order to see that waveform is, this is amplitude we're talking about here. So there's some maximum value A in amplitude, some negative maximum,